cardiovascular models, we mostly need data that define our geometries and our material properties. So the data that we use can be, for example, obtained from medical scans from specific patients, can be created by us, and the material properties can also be obtained from this kind of sources or from experiments. So we create these models with different goals. One of them is to analyze the cardiovascular system, how it behaves. For example, if you have a heart valve which is not functioning properly, we can create a model of it that represents its behavior and see how it's functioning. And we can also use these models to evaluate biomedical devices. For example, there's many studies which focus on the development of stents, which are devices that go inside the body. And these computer models simulate the behavior of the stents inside the vessel before it is actually put in a person. So these are two of the main focuses of cardiovascular models. And with all of this information, we are able to help doctors deciding on a specific course of treatment or surgery for a specific patient before he actually has the surgery. So how actually do these models, how are these models built? So the first step is to create the geometry. So this can be a patient-specific geometry, as I said, or it can be built using appropriate software. Here we see an example of a patient-specific geometry from a vessel, which was built from medical scans. Then we need to define the mathematical equations to represent the behavior which we want to study. For example, if we want to model blood flow through a vessel, there are specific equations which represent that behavior. So it is important to define these. Then obviously we also need to define material properties among other conditions. Afterwards we need to run the simulations and then we get some results. Here we see, for example, blood velocity on the left and wall shear stress on the right, which is a parameter I'll explain in detail further. Obviously, these results need to be further validated. So we use whatever material we have available. We can compare them to literature, to in vitro and in vivo data. So in vivo data is any clinical data which is available, and in vitro represents data coming from experiments. And we also rely on feedback from doctors to make sure that our computational predictions are in agreement with what they would expect. For this specific project and inside the large field of cardiovascular modeling, we focused on one specific tool, which concerns computational fluid dynamics, or CFD. So CFD focuses purely on the study of blood flow, and it's represented by specific equations that define that behavior. Actually, CFD has a lot of advantages because, for example, it allows us to measure parameters which cannot be measured in any other way. For example, wall shear stress, which I mentioned before, which is a measure of stress on the vessel wall caused by the passage of blood flow. CFD also has very good temporal and spatial resolution in comparison with the current imaging modalities from the hospitals, and it lets us study complex flows. For example, in this video, this is the velocity of blood flow through a bifurcated artery. And if I show you the passage of blood flow through time, you can definitely see that there's the formation of some vortices happening later on the time. So these kind of models are useful to study these behaviors. So for this project, we use CFD, but what is actually the purpose? What is the problem we are trying to study? So that concerns the process of hemodialysis. Hemodialysis is used for a patient when we want to help him filter the blood properly. So you have a patient and the kidneys are not working properly. So the function of the kidneys is to filter blood. And when they do not work properly, they need help. And the help that is provided in this case is through the process of hemodialysis, where we use a specific machine outside the human body that filters the blood for them. So in this process, we use a specific biomedical device called catheters. And for this presentation, I'll focus on a specific type of catheter, which is a central venous catheter. I'll explain to you using this video how a catheter is inserted. So we start by inserting it through a vein on the neck. And I'll stop here. This tip, which you see in this bubble, this is the catheter tip, and it's very important for this process because there are many different types of tips in the market, and different types of tips have different performance in this process of filtering blood. But I'll go into further detail on this later on. So the catheter is inserted through the tip, through the vein, and goes all the way to the heart. So you can see this is the heart, and the tip is located in a chamber in the heart, which is called the right atrium. So it is located there, and it stays there. And that's where it will help filtering blood. So basically, the catheter has two different lumens, one which brings filtered blood into the heart, and another which will retrieve unfiltered blood away from the heart. So if you look at the image on the right, this is the kind of setup which happens to these patients. So the catheter is located in this, it's placed in this position, and then we have two extremities which will be connected to the dialysis machine. So the problem here is that these devices must meet a lot of requirements, and sometimes they are not actually all met. So one of them, for example, is that they need to have a very optimal flow rate so that a large amount of filtered blood goes back into the heart, and a large amount of unfiltered blood is retrieved away from the heart. Also, the tip needs to have optimum dimensions. It needs to be long enough to allow this filtering process to occur, but it also needs to be careful because it cannot touch the wall of the right atrium. Flow recirculation needs to be less than 1%. This means that, for example, the filtered blood that goes into the heart from one lumen should not return back into the other lumen, which is trying to basically suck unfiltered blood. So that amount of flow recirculation should be less than 1%. Then we need to avoid kinking of the catheter segments, meaning that they should not be deformed. And we also need to avoid clotting at the tip. And this is actually a very important thing. The clotting basically means the creation of coagulants of blood at the tip, and it will create basically a barrier for the passage of blood flow. So imagine that your flow is passing, and then you are constricting that amount of flow which can pass. So we need to prevent clotting from happening to have a good performance of the catheters. And as I said, these requirements are usually very difficult to meet, and there are many problems which persist with the use of catheters. So some studies say, for example, that they are the least desirable form of access because they can cause high rates of infection and dysfunction in the human body. Other studies say that sepsis-related death is 100 times greater in these patients than in the general population. And then we also know that the design of these catheter tips can influence the creation of clotting and the replacement rate, meaning that these tips or these catheters can be replaced many, many times throughout dialysis procedures. So these are the type of problems which need to be solved. Now, to help solve these, catheter designs are usually evaluated through different ways. One of them concerns the setup of an in vitro experiment or a proper experimental setup, which concerns the simulation of blood flow using other different materials, for example, passage of water through specific tube chambers to represent the native environment. However, as you can see in this picture, this seems like a very complicated setup to have. And actually, these equipments are quite expensive to acquire and maintain. So another possibility is to use cardiovascular modeling, and this allows us to study the behavior of the catheters without them being actually implanted into the human body. So this picture here represents the patterns of blood flow as well as the velocity magnitude through various tips, and they can give us information on how the catheters are behaving. And the problem with this is that there are some studies which focus on the use of models to study catheters, but they don't actually take into consideration the right atrium. So they just model the catheters inside simple tubes. However, this is not enough to know if actually the behavior is appropriate. So according to that, our study focused on first developing a CFD model of the right atrium and validating it against appropriate literature data. And then we used this model to incorporate 4 different types of catheters and evaluate their performance. So the first step in the simulation setup was to define the geometries. So the right atrium, as you can see in this figure in the left, is this chamber. And to represent this chamber, we got our model, which is in blue. So for the right atrium, we have two veins where flow enters, which are the inferior and superior vena cava, or IVC and SVC, and then another exit, which is the tricuspid valve. Also, all of these models, the right atrium and the catheters, were set up and simulated using ANSYS Fluent. Then for the designs, we chose 4 different types of design. So A and B are step tips where they have the same design except that A has side holes while B doesn't have. C was a split tip and D is a symmetric tip. So all of these designs were placed into the right atrium similarly to what is presented in the image in gray. And as you can see in an enhanced closed up to the tip of the catheter, we have 2 lumens. So one represents the inflow, which is where filtered blood goes into the right atrium, and the other represents outflow, where unfiltered blood comes outside of the right atrium. So using these geometries, we studied 2 different things. First, we focused on studying the performance of different designs. And then we also decided to look into how different placements of the tip in the right atrium have an impact on their performance. So for A and D, we placed them in different positions just to see if their performance was similar or if there were changes. So for the simulations, we also had to define specific conditions. So as you know, your heart beats many, many times throughout a minute, for example. And to represent that pulsatile behavior, we had to include temporal profiles of pressure. So for the IVC and SVC, we represented the pulsatile flow through these 2D plots. And for the tricuspid valve, since we did not have any information to model it at the time, we assumed the pressure was 0 Pascal. For the CFD model, the walls of the right atrium were assumed rigid, meaning that they stay fixed during the whole time. And then to insert the catheters, the same conditions were used for the right atrium. And for the catheters, we employed inflow and outflow within clinical guidelines. To model blood flow, so there are many different types of models. I'm not going to go into detail in this, but basically we modeled blood using the governing equations, which are the Navier-Stokes equations. And then, as you may or may not know, blood is a soup of different components. So we have different things hanging in there. And their behavior affects the material properties of blood. So the red blood cells, for example, they behave differently according to different stresses that they are subjected to. And because of that, they have different viscosities. So we had to apply a non-Newtonian model to represent their behavior. In fact, we did a comparison between a purely Newtonian, which is a fixed viscosity model, and the non-Newtonian one, and we saw that there were some differences. So definitely we had to employ a non-Newtonian model in this case. Then we had to create a mesh. So a mesh is basically a division of the geometry into small geometrical parts where all of the equations of flow will be solved. So this here is an example of the basic geometry which we used. And below we have the same thing, but divided into many small mesh elements. So if we look closer, we can see that larger elements were used for the atrium and smaller ones were used for the catheters. This is because the catheters are obviously smaller in dimension, so they had to use a larger amount of elements. So for each of these tiny elements, we had to solve blood flow equations. And then what the solver does is, in the end, it compiles all the information together to get us the results that we want, either its velocity of blood or just to study the patterns of blood flow. For this creation of the mesh, I won't go into detail. I'll just want to tell you that the more elements you use, the more accurate your results will be, because you're approximating the geometry better. So we had to choose a good amount of elements to represent the geometry properly. And in the same idea, we had to run several heartbeats, or in this case, several cardiac cycles. So the more cardiac cycles you simulate, the more accurate your results will be. So the relative error between the latest cycle and the other ones will decrease. So we also had to run several cycles per model to have more accurate results. For the catheters, we also had to add another level of complexity. So we had to include a multi-phase model. This means that the blood going in through one lumen was modeled as one phase, as you can see in the red side. And the blue side was the blood going out, which was modeled as another phase. So this added another extra set of equations to solve. So in the end, we ended up having a complex model where we had to simulate 5 cardiac cycles. We had a very large number of mesh elements, several thousands. Actually, the catheter models were about 3 million elements, so you can have a notion of the amount of complexity here. The multi-phase model again added another set of extra equations to solve, and the results that were outputted by the models were very large. So our savior was obviously BEAR resources. To run the simulations, we used BlueBear, or high power computing, and to save all of these large file results, we used the HardDS. So the results that we were interested in obtaining were, first, for the atrium, were vorticity. So this is an example of a vortex flow being formed in a different vessel. So you can see that as flow passes, there's the formation of specific vortex occurring. So we wanted to quantify this behavior in the right atrium as well. Another parameter which we studied was the wall shear stress, which is again a measure of stress on the wall as blood flow passes. So you can see here that yellow and red colors represent higher shear stress, wall shear stress, and it occurs as blood is going through. For catheter performance, we quantified the recirculation, which is the amount of filtered blood that goes back into the other lumen of the catheter, which we don't want to occur. So in this video, this is an example of that. The red phase is the filtered blood going in, and we will see some spots of it coming backwards into the other part. So these tiny light blue spots are that phase returning back, which is what we don't want to occur. And then we also quantified the shear stress at a volume created at the tip. And that volume is represented here by this block. So for all catheter models, we created these blocks to get that quantification of the shear stress. So for our results, we first validated the right atrium results. So here on the left, we have the blood flow patterns within the right atrium and the magnitude of the velocity as well. So we can see that as flow goes in, it starts immediately creating vortex within the right atrium. And if we compare this kind of behavior with clinical data, which an example of it is on the right, we see that it's quite a similar behavior. So we were quite happy with that. So also the time average velocity was within in vivo ranges, and same thing as the time average pressure, which was in agreement with clinical guidelines for this kind of model. Then we also looked into the time average vorticity and vertical behavior. So the time average values were within in vivo predictions, and there was also the presence of helices, which gave rise to an helicovoltical pattern, which is also in agreement with what has been seen before. Interestingly, the vorticity and motion stress had similar temporal trends. So we can see that on this plot, they have a similar behavior throughout time. And with for example, a Pearson coefficient of above 0.7. And this is interesting because it means that if we are able to predict one parameter, we may get information on how the other would behave. And this can be interesting to get further insights into how the right atrium is actually behaving. Then after inserting the catheters, we also started by looking into velocity of flow and blood flow patterns. So here on the catheter B, we can see that there is flow coming in through the upper lumen, and then this amount of flow is returning backwards into the other lumen, which is what we don't want to occur, but I'll deep dive into it later on. And for catheter C here, we have a video just showing how the flow that comes into the atrium is mixed with the flow that's already there. So this is a really cool video which allows us to see how actually all this mixing occurs. Another thing which we looked into, but we didn't look a lot because we didn't have a lot of information to compare with, was to monitor the amount of flow coming from the catheter and entering the tricuspid valve. So the thing is, if the flow enters tricuspid valve, it means it's going into the rest of the left heart and then throughout the body. So this actually shows the amount of filtered blood that goes into the human system. So here we see that there is flow coming in. So these red spots appearing are the filtered blood going through the valve and going into the rest of the system. Unfortunately, we didn't have a lot of data from literature to compare this with, so we left this aside. But in any case, it's an interesting thing to look into in further studies. Then, introducing catheters in the right atrium altered vorticity. So the vorticity was increased inside the right atrium in comparison with the model alone. So in these plots, you see the right atrium curve is the blue one. So this is vorticity over time over one cardiac cycle. And for all catheters, that value, that temporal profile is increased. However, different tip placements did not impact on vorticity. So on the figure in the right, we have all the different types of placement which we tested, and the temporal profiles are quite similar. So different placements did not affect this. Previous studies have actually shown that elevated vorticity can be associated with problems of blood flow through the heart. So if you have a lot of vorticity, the flow may not behave properly. So this can be associated with other further issues. However, it will still need a bit of validation afterwards. So this is just a speculation at this moment. So introducing the catheters on the model also increased wall shear stress in some spots. So as you can see, for all of the catheters, there is a red distribution of wall shear stress. For example, for catheter A position 1, we have a large amount of elevated wall shear stress at the center of the right atrium. The same thing happened for the time average values. So the largest increases were seen for design D with 11 and 15% of increase, which is quite a lot. And then, in addition to that, for catheter A, for example, there were the creation of novel sites of increased wall shear stress, as given by the circled areas. So wall shear stress is a parameter which can have an impact on the changes in the mechanical properties of vessel walls, as previous studies have shown. So if these increases occur with catheter placement, maybe it can be the indication of some problems which may occur with changes in the biomechanical properties of the wall. So this would need to be further verified in future studies again. Then we looked into the recirculation part of the catheters. So this figure actually shows a time average value presentation of fractional filter, how different catheter designs and different placements give rise to different mixing structures within the right atrium. So for example, catheter C allows for a very good mix of all of this catheter flow in the right atrium, while for catheter D in the first position, the majority of flow goes through the dark whisper valve, so it doesn't get mixed properly in the right atrium. Anyways, we saw that there was flow recirculation in all of the designs, with the step tips, catheters A and B, giving rise to the worst results, with recirculations above 5% for catheter A and of 45% for catheter B, which is quite a lot. On the other hand, catheter C and D had the best results, with D complying with that design requirement of less than 1% recirculation. So these results tell us that the presence of side holes in step designs are important. If you remember, the difference between A and B was the presence of side holes on catheter A. So it allowed the flow to be a bit more spread and not return back into the other lumen of the catheter. So we can speculate that the presence of the side hole are important for this kind of catheter performance quantification. Again, different T placements gave rise to different recirculation percentages, and we can also see in this picture that the mixing flows are different according to different positions. And position closer to the wall gave rise to worse recirculation percentages, meaning that if you place the catheter in a specific position, it will have definitely an impact on its performance. We also looked into shear stress at the catheter tip. And again, we saw that the worst results were with step tips, A and B, and the best results were with C and D. And we can also see here on the plots the temporal evolution of the shear stress. So for all catheters, the shear stress was above 9.75, and different tip placements gave rise to different shear stresses, again, as we can see on the plot on the right. So this kind of result is worrying because higher high shear stress, specifically above 10 Pascal, is assumed to activate platelets and lead to thrombosis, meaning that it can further enhance that clotting at the tip, which we want to prevent. So this picture here gives us a better visualization of this. This is the shear stress between 10 and 20 Pascal. And we can see that there is basically shear stress within this range in all of the lumen exits and side holes, which is a bit worrying because this gives us the hint that there may be a potential for clotting formation in these regions. So definitely this needs to be looked into. So according to all of these results, the main study findings that we have is that the symmetric design, or the catheter D, gives rise to best performance outcomes, while the step designs A and B give rise to worst design outcomes. However, this study had several limitations, and therefore we leave these as future directions for future work. So the first one would need to have into account patient variability. In this study, we just focused on a generic right atrium geometry. However, no two patients have the same right atrium, and therefore it is important to see how different right atrium geometries will affect the performance of these catheters. Also, we need to have into account the movement of the right atrium wall. In this case, it was assumed fixed, but in reality, it moves with every pulsatile flow coming in and out. So we need to account for this behavior. Here I have an example of another vessel, and this is the deformation of the wall as flow goes by. So you can imagine actually how movement of the right atrium wall will have an impact on blood flow through it. And then in the same idea, we should also account for movement of the tricuspid valve. So the valve was kept not modeled, but in reality, it would look something like this. So this is another different heart valve. We change the blood flow profiles. So we need to account for these different aspects in the future. So to conclude, according to the outcomes of our study, we realized that having a realistic right atrium model is actually essential to studying catheter performance, and also to have into account its interaction with the right atrium environment of blood flow. So we need to account for this to see how it would impact on multiple hemodynamic parameters. Oh, sorry. Also, we need to take into consideration that the correct tip placement in the right atrium is essential, as it will improve flow circulation and decrease shear stress. Currently, there are different medical guidelines for this placement, and they are in disagreement with each other. So they need to reach a consensus on where exactly to place the catheter tip to have good performance outcomes. So thank you so much for listening. And obviously, if you have any further questions, you can contact me through this email, or you can talk to me right now, write in the chat, and I'll reply to you. Okay.
Thank you for Olivia. It's very interesting, and it's a little bit hard to understand for me. But it's quite informative.
Thank you.
Thank you very much. Is any other questions from the others? And you can tap, or you can raise your hand, or just mute yourself and you can ask. Anybody? Okay.
I would prefer if someone has questions to write on the chat, so that there's no problems of internet connection or anything. Okay.
Okay, there's a question. Say, you spoke of the future ideas for the model, and would the movement of the catheter also be something to look into in the future from the casted?
I will answer, and then there's another question also from before. So Kadi, thank you so much. Yes, so in theory, we should account for movement of all these structures. So the atrium wall, the valve, and then also the catheter movement, which several studies have shown has also a big impact on the performance of the tip. However, accounting for the movement of all of these structures at another level of complexity. So for this model, we were just, let's say, we were focusing on solving equations for blood flow. But to account for movement of catheter, for movement of the wall, for all of these things, we would need to add another set of different equations. And that even with bare resources, it would be very difficult to have results within a good amount of time. So this is definitely something to look into the future, but it would need a lot of work development to have a full model working, which would incorporate all of these features. Okay, from before, very interesting talk when you start looking at human testing. So that's the tricky part. It's very difficult to have clinical trials with this kind of biomedical devices. So for this project, we collaborated with an industrial entity, and they build actually these catheters. So they have an in vitro setup, an experimental setup in their building, which tests the behavior of these catheters as it would be on a native environment. So they have a lot of chambers and tubes connected to represent the human body. When we would start having clinical trials or looking at human testing, it's a question which I cannot answer at this point, because it's a very tricky thing. Right now, the industry, it's so focused on just using experimental setups that even computational modeling is a very novel thing. It only started appearing applied to this some years ago. So I think there's still a long way to go before we start looking at human testing.
Thank you. Thank you. And I have a quick question, but it may sound stupid. But I mean, you said the the model, the catheter model. So I'm wondering if the catheter model is varies from the people to people. For example, maybe it's suitable for a type of people, patients, but it's not suitable for others. So
yeah. That's one thing which we still don't know, because so there are different designs in the market, and these designs, they all look into meeting those specific requirements which I mentioned in the start. So optimal flow rate, optimal recirculation percentages, and all of these. So there are some long-term studies which have been done looking at how people using the specific designs, how they feel if the performance is good. But it's hard to say for a specific patient we need to use a specific design of catheter. So that's where I think computational modeling can play a role in the future. If there is a fast way of, for example, we have the model of the heart, of the atrium of a person, and we have different design options to choose from. If we virtually place them into the person's model and simulate how the blood will flow through all that and how the performance will be, then we can have a better indicator of, okay, this design is better for this person than another one. But to reach there, there's still a lot of things to develop in the model. There's still a lot of translational barriers to pass, because doctors usually have a bit of, they don't have a lot of confidence in these engineering tools. So we also need to convince them that these are clinically relevant and they can be useful. So I think that's a possibility in the future, but there's still a lot of steps to overcome to get to that point.
Yeah. So your model is based on the past data, yeah.
My model is based on, yes, it's based on data from past studies, so data that I found on the literature.
Oh, okay.
So the geometry itself, I found on it's an open source geometry, which is a generic model, basically.
Okay.
It was not, this model was not obtained from medical scans. But it can be possible. So future studies can definitely obtain that model from patient scans, from patient images, reconstruct to get the 3D geometry, and then use it as a patient-specific approach, basically.
Okay, thank you very much.
Thank you.
Anybody has other questions? Do you want to? No. Yeah, I guess maybe there's no further questions. Just you.
That's all right.
Okay, but thank you for your excellent presentation today. It's very interesting and informative. Thank you very much.
Thank you so much. Thank you.
Looking forward to your model to be applied in the future.
Hopefully in the future, let's see.
Thank you.
Thank you.
Have a nice day.
You too. Have a good rest of conference. I'll be around to see you also.
Okay, thank you.
Hopefully it all goes well.
Okay. And I think we can have the around 10 minutes break and until our next speaker, the Khadija. Is Khadija here? Hello?
Yes, hello, I'm here.
Yeah, I can hear you. And I think you can prepare your presentation now, and we can have a 10 minutes break, and we can return 11:30. That's okay for everyone.